Okay, so today is our great pleasure to have Professor Osman Khan to give us a talk. So Professor Khan now is an associate professor in electrical and computer engineering at Tufts University. His research interests include signal processing, optimization, and control of stochastic systems and machine learning. So his works have been recognized by several awards, including this prestigious NSF Career Award and this NF Re Award and several Best Paper Awards. So today he's going to talk about the distributed stochastic non-convex optimization. Okay, so Osman, I'll give you the control.
Thank you. Thanks, Yang, for inviting me. Thanks, Rongi. So it's my pleasure to discuss some of our recent work today. And I'm going to talk about these problems that we call distributed optimization. And I'll try to cast the problems in terms of some of the specifics that we have been considering in terms of problem formulations, results that we want to develop. And I also would like to kind of cast light on under what conditions the results that we have developed are optimal, and in what cases they can be potentially improved and stuff. So before I start, no good work can be accomplished without the help of our students. So I have had the pleasure of working with some great students who have contributed a lot to the presentation that I'm gonna present today. And most of this work is my second student who after PhD started working in Facebook and now in ByteDance. Most of this work is kind of associated to him, my student Ran, and my other student Fakta. So let's start. So I'll give a brief overview of what problems that we have been considering in our research. I'll try to motivate it, try to set up the problem mathematically, and then we can try to look at the nuances of the solutions, how can we improve, etc. So this is a typical, machine learning, supervised learning setup where we would like to learn from data. And you can, for example, consider problems such as, simple problems such as linear regression, more complicated problems such as binary classification, neural networks, etc., where our goal is to build a classifier, for example, that that declares whether a given image was, let's say, an image of a dog or a cat. So if we think of problems like this, imagine that the data over which we want to perform learning is available at several different resources. So these could be our phones. So our cell phones, for example, have a lot of images, cameras that are installed for security in our house, speech data that is collected by voice recognition type softwares. And in general, all of this data is located at different physical locations. So for example, in this figure, all of this kind of, I have shown this computer with a computational unit with a hard drive where these data sets can be located. And there are a few different models under which we perform learning. So for example, we would like all of this data. One way is that we bring all of this data to a centralized location. And this centralized kind of GPU or a collection of this big cluster machine would go over the data in order to perform some machine learning or AI task. But in general, you can imagine that collecting data to a central location has a lot of overhead. For example, my data is private. I don't want to share my data with a central entity because of privacy concerns. My data could be very large in size. So imagine that if you have a battery operated drone or a battery operated camera that is installed in your house, continuously transmitting data to a central server so we can do machine learning or whatever incurs a lot of cost. So methods that are of interest or that are of interest in my research group especially are these distributed methods where we don't share data, but every node, every device just performs local communication, local computation on the data. So solve, a small problem on their own data set, and then share information with the nearby machines to learn some global parameters. So for example, I'll motivate this with a very simple basic case study, and we'll dive deep into more complicated problems later. But imagine a simple logistic regression problem. My goal is to train a classifier that can distinguish between images of automobiles and images of airplanes. And we got these images, we got 5,000 images of automobiles from the CFAR10 data set and 5,000 images of airplanes. And these are small 32 by 32 pixel images. And if we train a binary classifier on this entire data set that is situated on a central machine, then this, the gray curve, the blackish gray curve tells me how the test accuracy of this trained model as a function of the CPU time. So the center that processes all of these 10,000 images in this logistic regression problem achieves 70% test accuracy in about 113 seconds. But if I have, on the other hand, 5 devices over which I distribute this data, so every device now has 2,000 images, every device performs some computation on their local data and then improve their knowledge about the model that they are training with the help of local communication, we can see that 70% test accuracy with this distributed training can be achieved in 49 seconds. So 49 compared to 113 is more than half of the improvement in terms of the CPU time. But remember that this improvement is coming at a cost of communication, because center does not have to communicate with anyone because it possesses the entire data set. But for these distributed problems, these nodes communicate with other nodes. So that is the missing piece. So we, of course, 49-second computation time plus some communication resource. So we would like to formalize these type of problems, formalize scenarios under which distributed methods perform out better than the centralized methods, right? So quantify this improvement, performance improvement, explicitly in terms of the problem parameters, in terms of the network parameters, etc. So this is the goal of the talk. So I'll try to formalize the problem mathematically now. So as an example, consider another image classification problem. So I have a set of images. The images either belong to a stop sign or a yield sign. So two these traffic signs. And I have a large collection of such images and they are labeled. So I know which one is a stop sign and which one is a yield sign. And my goal is to train a classifier that predicts whether a new image was a stop sign or a yield sign. And in order to do this training, so I do the simple, logistic or binary classification type setup where every image I convert into a feature vector in a high dimensional plane. So if, for example, in my previous example, if there were 32 by 32 pixel images, a feature vector is the pixel values of all pixel values. So that would be a 1024 dimensional feature vector, which we can reduce them to a compressed feature vector or focus on certain features like number of sides, edges, etc. But once we have the feature vector, all the stop signs are, let's assume, or let's say that they are clustered or grouped together in one area of this high dimensional space, and the yield signs are clustered in another area. I mean, that's our hypothesis in a way. And we want to build a model, we want to learn a model, which is this straight line or a hyperplane, such that this straight line distinguish or separates the two data sets in the best possible way. So here, for example, if you consider the red hyperplane classifier, we can give a score to it. So if you look at the red classifier, it misclassifies. So the classifier would say any data point, any image converted into a feature vector that lies above the classifier is a stop sign, lies below the classifier is a yield sign. And if I were to give a score to this classifier, one crude scoring would be that the red classifier misclassified 3 stars and 3 triangles, so the score is 6. However, on the other hand, the green classifier misclassified the same points, the red and green points before, but in addition also misclassified this green triangle. So its score is 7. So given all data, all images theta, their labels y, I can build a model y hat that predicts these labels, and I can compare them with the true label y in order to give a score to this classifier. And I would choose a classifier x star that gives me the best score, or that minimizes this loss function. So in this case, the loss of the red classifier is 6, loss of the green classifier is 7. So I would like to pick the red classifier, right? And when the new point comes in, a new image comes in, I can test the new image, whether it was a stop or a yield sign, just by seeing whether it's above the classifier or below the classifier. So among all possible hyperplanes that can do this, I would like to pick the one that minimizes the training error, in order to hope that the test accuracy will be improved down the road. So essentially what we are interested in is considering minimization problems or minimizing functions, where these functions in a machine learning context are loss functions that define or describe the loss between our model y hat, that is a function of the data that we are given, versus the truth y, and some loss function that is how we want to quantify the truth versus the model. And you can imagine that many different predictors or models, y hats, in combination with the loss functions, will lead to different properties on this cost f. So for example, people who are familiar with signal estimation or optimal control problems would realize that for linear systems, these classifiers are typically, these models are typically linear, and the errors that or the loss functions that we consider are quadratic. So we have functions, we could be interested in minimizing functions that are quadratic. In logistic regression problems, if we use some regularizer, we have strongly convex functions that we want to minimize. And in neural networks, reinforcement learning, blind reconvolution type problems, we are interested in minimizing functions that are potentially non-convex. So in this talk, my goal is to consider minimization of functions under different function classes, and the minimization I'll define as searching for a point x star such that the gradient at that point is 0. So this is the first order minimization criteria. And in this talk, I will discuss first order methods over different function classes to minimize such functions. And in the end, the underlying solving the underlying machine learning problem when the training data is distributed over a network of nodes. So again, data is not available at central locations, so I cannot just go and choose, stochastic gradient descent or one of these training methods. I have to make sure that, my method caters to distributed data. And then we would like to understand under what conditions the distributed training gives me the same performance as the centralized training, what other aspects of this problem we should consider, etc. Some basic definitions before I start describing these problems in more detail. So we consider problems where functions are L-smooth. And if you recall the definition of L-smooth functions, it is that the gradients of these functions are Lipschitz continuous. So it basically requires these functions to be differentiable. We also assume that these functions have some lower bound f star, which is strictly greater than minus infinity. So basically, they don't keep just going to minus infinity. This L-smooth condition does not require any convexity, and intuitively, we can think of L-smooth as functions that are bounded above by a quadratic. So in this figure, I'm showing a non-smooth function, which potentially has one global minimum, one local minimum, but this function is bounded above by this quadratic at every point, and if that is true, these functions would be non-convex and smooth. The kind of the growth of this quadratic is controlled by this factor L, and the smallest L that gives me this uniform bound becomes like the parameter L of this L smoothness. The next, we consider functions that are, in addition to being L smooth, are also convex. So convex is a very kind of well-known function class. So basically, what we require is that the function lies above all of its tangents, or if we take 2 points on the function, draw a line, the function lives below the line. And then we consider strongly convex functions. And strongly convex functions are functions that are convex, but it's also at the same time bounded below by a quadratic. So you can see that for strongly convex functions, we are basically eliminating the flat bottom, because it has to be bounded below by a quadratic, or it should have a curvature at every point. The growth of this quadratic from below is controlled by the parameter mu, and that's why we call them mu strongly convex. And for functions that are smooth and strongly convex, they have the smoothness parameter L, form convexity parameter mu. We can define condition number kappa, which is the ratio between L and mu. And you can see that because L is the quadratic that upper bounds and mu is the quadratic that lower bounds, L over mu is always greater than or equal to 1. And as an example, you can consider a quadratic function where it's a perfect circle. For example, x1 square plus x2 square has the condition number of 1. But if you go towards functions that are more elliptical, like L x1 square plus mu x2 square, they'll be upper bounded by L x1 plus L x2 square, lower bounded by mu x1 plus mu x2 square. So they'll have, the more a function becomes an elliptical, right, the more the condition number grows, because the upper bound is controlled by a bigger L and the lower bound is controlled by a smaller mu. For minimizing smooth and differentiable functions, so that is our goal. And we are basically interested in searching for a stationary point x star where the gradient is 0. And you probably know that for different function classes, this condition that the gradient is 0 leads to different properties on on the stationary point. So for example, in non-convex problems, a stationary point where the gradient is 0 could be a minimum, could be a maximum, or could be a saddle point. For convex functions, we know that the value of the function at this stationary point is the unique global minimum. And for strongly convex functions, we know that the point at which this unique global minimum is achieved is also unique. And you can see these from these, in the figure examples. The red curve has the unique global minimum, but it is achieved at many different points in these triangles, where for strongly convex functions, unique global minimum achieved at a unique location x star. So depending upon that we are searching for a stationary point, depending upon the context that under which function class we are searching for these points, will lead to different properties on these points x star. So first order methods, I'll briefly, I'm sure everybody knows that, so I'll try to go fast, but basically we are interested in first order gradient based methods. And the intuition is very simple. So if you look at a function f of x, the intuition is that if you compute the gradient of this function at any point, if you move away from the positive gradient, so in other words, you move towards the negative gradient, you are decreasing the function value. So that's the basic intuition, right? The basic intuition is that the function is increasing in the direction of positive gradient. So if we move in the direction of the negative gradient, potentially the function value decreases. And that decrease is monotonic if the function is strongly convex. But for other cases, we know that if you take a step in the negative gradient, you cannot increase the function value. And it basically leads to a simple algorithm. So my search for x star would be start at any point xk on the function, evaluate the gradient, and then find a new point or a new estimate of x star by moving away from xk in the direction of the negative gradient. And that becomes my new point xk plus 1. And we know that the function value f at this new point is less than or equal to the function value at this old point. And this inequality could be strict given, a more kind of decreasing function. And in terms of this gradient descent method, if I look at different function classes, I know that gradient descent converges to a first order stationary point x star that satisfies this property that the gradient at that point is 0 at a certain rate. The rates that we can guarantee is that for a non-convex function, the gradient, the norm of the gradient goes to 0 at the rate of 1 over square root of k. For convex function is 1 over k. For strongly convex functions, both the error between, xk minus x star and the function difference, they both go to zero exponentially fast, linearly on the log scale. And these rates are non-stochastic, not accelerated. So we can improve these rates if we add, for example, some acceleration based on momentum, Polyak or Nesterov, etc. So I've given you a brief intuition of what gradient descent is. Given you some context of the rates so this rate depends upon the problem when this entire gradient f, which is basically, you remember, f is a function f is the loss function that encodes the loss between my model and the truth, and the model depends on data. So up to here, this gradient is computed this gradient is computed at a location which has the entire data set. And how do we extend these methods to distributed problems when data is distributed among many resources? So we can consider a simple linear regression example. So suppose we have a collection of these 18 or so points. One agent has the magenta points, one is blue, one is orange, one is green. So you can see that if I look at the collection of all of these points, the true line is this black linear regression line. But when every node has its own data, their estimate of the linear regression line could be way off than the global truth. And if every node were to implement, so f of I here is the gradient of the loss function that is dependent on the local data. And if every node were to implement gradient descent based upon its local data alone, what they learn would be, in general, 4 different values of slope and intercept, for example, which will not be anywhere close to the global truth. So the local gradient descent, in which I do not look at any other node in the network, I just do my own thing, in general will not agree on the same solution. And since they're not agreeing on the same solution, they cannot agree on the optimal solution. So requirements for a distributed algorithm would be that I want agreement. I want all nodes to agree on the same solution. And I want optimality is that the agreed upon solution should be optimal. So I will give you the first, one of the early works on distributed optimization or distributed minimization problems. And we'll first restrict ourselves to smooth and strongly convex problems with full gradient. So there's nothing stochastic for now. And this is the problem formulation. So I have a bunch of nodes in the network. Every node possesses its own local data. That local data leads to a loss function that we call f of I. So f of 1, f2, f3, etc. And I want to minimize the loss across all data points. So I want to minimize the total loss, sum across all loss functions. And these nodes are allowed to communicate or exchange information with their neighbors according to a certain topology. And the problem assumptions are that each f of I is private to node I. So no node is allowed to share, or no node would like to share its own personal data with nearby nodes. Each f of I is smooth and strongly convex, and the nodes communicate over a connected graph. Connected, I mean that if you pick any 2 points in this figure, they have a path between them. So the underlying graph is connected. You can see that certain nodes can only exchange information in one direction. So the graph does not have to be undirected. It could be a directed graph where information flows in a certain direction. And this, under the conditions of that each local function is smooth and strongly convex, we know that the global function uppercase f has a unique global minimizer x star at which the gradient is 0. And the first algorithm, or the early work on distributed optimization, is this mix and descent algorithm, in which node I instead, so if you ignore the red term, you can see that this is just local gradient descent. So I'm just implementing gradient descent on my data. But what mix and descent does is that, so if we look at the bottom figure, node 1, the magenta node, asks for for this classifier or the model information from the nearby nodes, and then combines them, and then takes a step in the negative gradient direction that is based on its own local data. The weight matrix, so this combination, this linear combination, is sum preserving. So basically the numbers, these W's are greater than 0. Sorry, they are non-negative and they sum to 1 across both rows and columns if I combine them in a matrix. And what we can show is, what has been shown is that this algorithm, distributed gradient descent, DGD, converges linearly up to a steady state error. So the error goes down linearly and then becomes flat. So remember, gradient descent, error goes down linearly to 0. And exact convergence, where the error goes to 0, can be achieved with the help of a decaying step size alpha. So alpha is not a constant, but let's say something like 1 over k. May not be exactly that. But with a decaying step size, we can achieve convergence to the global x star, global optimum x star, but at a rate that is sublinear. So it's not linear. And this is how it looks like if we just distributed gradient descent, which is on central data. The error keeps decreasing linearly on the log scale or exponentially on the normal scale, and the error goes to 0. But with distributed gradient descent, the error comes down linearly, but then settles at a steady state error. So there is always this error. So how do we, so of course the natural question arises, how do we remove the steady state error? And this is where our work, distributed gradient descent with gradient tracking, becomes relevant. And I'll put it in context also with respect to what others have done before us. So again, the problem is we want to minimize the sum of local functions. These local functions are depend upon local data set. In other words, you want to search for a point x star that is the first order stationary point of this problem. And distributed gradient descent, it does not reach x star, or it always have a steady state error, is because x star is not a fixed point of this algorithm. By that, what I mean is to look at the algorithm that I described, the distributed gradient descent, and plug in x star here and plug in x star here, then the first term on the right-hand side of this equal sign is x star because the weights sum to 1. However, the second term is not x star because the gradient at x star is not necessarily 0. The gradient is 0 at the sum, right? So even if this algorithm starts at x star, we don't end up in the next step, we lose x star. So, and we call this problem, so you can imagine that if this gradient of fi, if this fi were to be capital, the uppercase f, then the gradient of uppercase f, which is the sum, is 0 at x star. So how far each local fi is from the global f, or the sum, is the local versus global dissimilarity. And we quantify this with respect to some constant eta. And there's a more formal definition of this. And because this eta is not 0, that eta kind of drives this the steady state error in DGD. How do we fix? We can think of a fix where we replace the local gradient, which is the gradient of fi, with another variable y that tracks the global gradient. So intuitively, I'm not taking a step in the direction of the gradient. I'm taking a step in the direction of another auxiliary variable y, where y asymptotically tracks the sum gradient, or the gradient of the uppercase f. And so this technique was introduced for undirected graphs in December 2015. Over directed graphs at this more or less similar time, we presented an algorithm that we called AB algorithm, and this is how the algorithm looks like. So we perform the basic step of DGD, distributed gradient descent, but in the direction of an auxiliary variable y, which is updated using this bottom equation. And you can show that this bottom equation basically converges to the sum of the gradients, and essentially this y is basically converging to the sum, and the original problem kind of converges. We established that this algorithm converges linearly on the log scale to x star with the introduction of this gradient tracking equation. And these coefficient a's and b's, if you remember from before, these were the matrix that collect these coefficients. It was sum to 1 across both rows and columns. Now the matrix A that collects AIR has to be row stochastic, and the matrix B only has to be column stochastic. So we were able to relax these conditions as well. and we can add momentum terms to these to see acceleration. So there is a lot of work on this AB algorithm, which is applicable to both directed and undirected graphs, because we don't have the doubly stochastic restriction on the weight design. And there is several results that have been developed. There is interesting work on mean connected graphs done by Shipu and Angelia Nedich. Our work was on time varying random graphs. There is another group that considered, I think, Scuteri and Themis, Charalambos, and Alto that considered asynchronous problems. Mike Rabat considered asynchronous problems, etc. Interestingly, condition number dependence of this AB algorithm, which is this distributed algorithm. So if you know gradient descent, which is centralized on centralized data, condition number, so this is smooth and strongly convex problem. So condition number is the ratio of the smoothness parameter and the strong convexity parameters. For gradient descent, this dependence is on with kappa. AB undirected, this dependence is kappa 5 or 4. AB directed, which I presented here, is kappa square. Empirically, we have noticed that this kappa square dependence can be reduced to kappa, and there is some work which has shown this dependence going down to kappa, but for over undirected graphs, and I think similar ideas could be extended. If we add momentum, we can improve this kappa. So gradient descent with momentum is kappa square root. Over undirected graphs, people have shown, Guanan and Nali at Harvard have shown the rate kappa 5/7. With Nesterov momentum, we have done some work where we have shown convergence for the heavy ball momentum, but several aspects of these problems are not analytically shown, and I'm happy to discuss in detail if there is interest later. This is how the performance looks like. So remember, purple is the distributed gradient descent, which converges with steady state error. Black is the gradient descent, which is on centralized data. If our algorithm AB, which adds gradient tracking now, recovers linear convergence. And if we add momentum to AB, heavy ball momentum, we recover this blue curve. And of course, if we add heavy ball momentum to the centralized gradient descent, we can recover this red curve, which is much faster. Excuse me. So addition of gradient tracking recovers linear convergence. This we have proved. Acceleration, that it is faster than without acceleration, is only shown numerically but not proved yet. So in the distributed case, for the AB algorithm, both heavy ball acceleration and Nesterov acceleration are still open problems. And what happens when these gradients are imperfect, which means that these gradients are stochastic. So by that, I mean that instead of evaluating the gradient of the function fi, we evaluate the gradient of the function fi, but we receive a noisy version. And if we have noise on those, so if you remember, gradient tracking is this blue line, which basically overcomes the steady state error in distributed gradient descent. And this is the centralized gradient descent. With noise, pretty much everything kind of goes out of the window, and none of the algorithms converges to the truth, which makes sense because we have a constant noise coming in. Analytically, we have this result which quantifies the steady state error of stochastic gradient descent, distributed stochastic gradient descent without gradient tracking. And you can see that the result depends upon nu square, which is the variance of the noise, eta, which if you recall was the global versus local bias. And what happens is the gradient tracking eliminates eta, so eta dependence goes away from the steady state error, but nu square still remains. So we need to find methods or ways to be able to address this variance in order to converge with zero error. So this is where I would jump to stochastic optimization, distributed stochastic optimization, non-convex problems, and perhaps also show some of the strongly convex results in the process. So we want to minimize a uppercase f of this global function, which is which is decomposed into a sum of local functions. Every local function is basically depends on data, And we can consider this into two cases. So imagine a scenario where you have a robot and in real time you make measurements of a certain phenomena. So given an X and RP, each node I makes a noisy measurement GI of the local gradient Fi. And the other scenario is this batch context in which we possess the entire data set at one location. So my cell phone has, I don't know, 30,000 images, and I have all of these images, at one location. So these are the two measurement models that we would like to consider. And in the communication sense, these are the models that are relevant. And I would give quick. So for example, think of a data center. In a data center, we have a very controlled environment. We have a lot of, high performance computing machines that can interact with each other over, certain fixed topologies in a very consistent manner. And typically we have a smaller number of machines, but each machine has a very large number of data stored, and topology of how they communicate is controlled, versus you think of, an Internet of Things system where we have, cameras in our house, or I don't know, smart devices in terms of our, lights and electric car and whatever. In this case, you can imagine that typically we have a lot of battery operated devices. Storage is limited, and communication is limited. They are typically over an ad hoc topology. So in the IoT regime, we define it as a regime where the number of nodes in the network is very large, and they communicate over an ad hoc topology. And I'll try to give results for these theoretical results for these different kind of regimes. And in summary, if you remember, gradient tracking allows us to eliminate eta, and this local versus global dissimilarity bias was eliminated with the help of this gradient tracking. And now we want to see under what conditions or how we can remove this new square, the variance dependency. Can we quantify such improvements? Can we eliminate the steady state error due to the variance? And what can we say about these different function classes that I introduced? And here I'll talk about batch problems. We have work for other problems we can happy to discuss later. Batch problems is the case where data is available offline. So that is when I have a collection of images already stored in my computer, my hard drive, and I want to train on those images. So there is no real-time element of collecting data. So I describe this, the batch framework again. So imagine I have n nodes and I want to train a classifier that distinguishes between several different animals. So node 1 possesses all images of, let's say, elephants. Node 2 possesses images of a dog and a wolf. Node 3 possesses some images of a lion. And node n possesses, a mixture of images across different animals. The point with this, data distribution is that the data distribution is heterogeneous, which means that if node 1 is training alone on its own data, because it has always seen elephants, it will never be able to distinguish between elephant, and all these other image classes. Only when you combine all of these images together, we'll have enough, images with respect to all different types of classes. The number of data points also is not necessarily uniform. So local gradient computation, if I were to do gradient descent, right, will require in a distributed, let's say, setting, I will distribute to do a local information fusion operation and then take a step in the direction of the local gradient. But remember that the local gradient is to be computed across the entire local data set, which if the local data set is large, then will take a very long time. So traditionally, the solution is that we don't take the full gradient. We sample an image from this local data set and we compute a gradient of this sampled image. So here this tau depends, tau is basically a random number generated between 1 and mi, where mi is the total number of images, let's say at node 1. And tau will be to randomly just select one image, compute the gradient there, take the step, implement gradient descent, repeat the process with another randomly sampled image. And remember, in this scenario, the performance is impacted because, first of all, I have the sampling issue that I'm not implementing the entire local gradient. So variance will be in effect of this sampling process, and also local versus global bias, because even if I implement the entire local gradient here, I am much farther away from the global gradient, which is across the entire data set. So our work was to introduce this gradient tracking plus variance reduction framework, where we go from a sampled gradient at node I. So this gradient is sampled at node I, and across my entire data set, I just pick one image randomly. And this framework allows me to grow from this local sample gradient to the global gradient of the entire data set. So there are two steps in this process. One is called local variance reduction. So first I sample one image, but then from that sample, I try to estimate the entire local data set, right? So this semi approximate equal sign tells me that this VI is an estimate that I have generated from local samples, and it's estimating the sum across all local data. And then the next component is that gradient tracking component, where I fuse these estimates VI over the entire network, as I did before, over true data, over non-stochastic data, to learn the global gradient. And the combination of these two, you can see that different methods for estimating the local gradient over the entire local data set with samples, and different fusion methods over the network will lead to different algorithms, and these different algorithms have different properties when it comes to different models that we consider. So here I'll show you two instances of this framework. One is called gradient tracking with Saga-based variance reduction. One is called gradient tracking with the Sara-based variance reduction. So the Saga-based method is where every node starts with a seed. So x0i is where I randomly start my algorithm. At this algorithm, node I computes the gradient at every data point. So imagine it has 5 data points, 1, 2, 3, 4, 5 images. And then it estimates the local gradient with respect to these data points. Then it does some mixing across the network and update the state xi. At the next time step with this x1i, it only draws samples one gradient, updates it, and then recomputes, repeats this process where estimates the entire gradient, local gradient, then mix over network, update x2. So this process, you may be able to see that requires storing a gradient at every point, at every data point at node I, because that allows it to kind of take one slice out and replace it with another, with a gradient evaluator, the new iterate. And for smooth, strongly convex problems, we have shown in several papers that these algorithms converges linearly to the truth. For non-convex problems, we have shown that these algorithms achieve linear speedup over their centralized counterparts. By linear speedup, I mean that they are order n faster than the centralized algorithms, and their performance is independent of networks. So for example, whatever topology it is, their performance does not get impacted by the network. But more importantly, these results of linear speedup and network independent, they are achievable in a certain regime. And those regimes are corresponding to, you remember that big data regime where I say that every one of those two regimes, big data or the IoT regimes. In the other GT variance reduction framework, which is GT-SARA, this framework does not require storing gradients at every node, but it requires network synchrony. So I'll describe what it means. So imagine node I has m sub I data points, so m sub I images over which node I would like to train, and node R as m sub R images. So first node I computes the gradient. So at given an iterate x capital X uppercase T at node I, it computes the gradient of the entire data set and then runs these iterations. So the iterations are: you sample one of the images, updates the gradient, then mix over the network, update the iterate, and then sample, update, etc. And node R, remember, is doing the same. However, the process is repeated every capital T iterations. The process of computing the full local gradient is repeated. So for example, imagine that node I has 10 images, m sub I. So node I has to compute these 10 gradients to start the process at time t, time 2t, time 3t, time 4t. Node R, on the other hand, imagine it has 1 million data points. So node R computes 1 million gradients, and then it goes t steps, computes 1 million again, goes t steps, etc. But because the seed, right, which is this periodic computation of the full local gradient, is repeated at every node, however, the time that it requires to compute these gradients at each node is different because the data size can be different. So a lot of nodes in the network could be sitting idle if the amount of data at each node is different, or their computation capabilities are different. So this aspect of this distributed algorithm does not require storing data at every node, but requires synchronization among the network, where I know that I have to wait until everybody in the network computes their local gradients, etc. So this trade-off between Saga, the first instantiation of variance reduction versus the second instantiation, is often considered as a space versus time trade-off, where the first algorithm requires storage, while the second algorithm requires network synchronization. We have shown for non-convex problems that GT Saga is state-of-the-art or results into the best known convergence results for ad hoc networks or the IoT regime, while the second one, GT Sara, is optimal for the big data regime. And I'll show these results. I skip this slide, but basically here I'm saying that if xki is the iterate generated by the GT Sara algorithm, which basically uses gradient tracking and Sara-based variance reduction, then this algorithm converges to the first order stationary point condition in probability, almost surely, and in mean squared. But more importantly, if we consider the batch problems where I would like to, where the data, where let's say that I would like to minimize a sum of non-convex functions, which are n times m. So basically I have n nodes and m points per node. So I would like to minimize the sum of nm non-convex functions, smooth. We could ask this question: how many gradient computations are required to reach an epsilon accurate solution? So this is the result, but where h tells me the number of computations that are required when the inner loop of GT Sara is order m, where m is the number of data points at every node. But I'll simplify this in the next slide. In a certain regime, which is described by this equation, that the number of nodes is less than equal to the number of data points times 1 minus lambda to the power 6, which is a graph topology based metric, then the number of gradient computation required is capital N square root times 1 over epsilon in order to reach epsilon accurate solution for this non-convex problem. What we know is that this rate, which is achievable in a certain regime, which we call the big data regime, matches the centralized algorithmic lower bound that was derived for this problem class, which basically shows that the distributed algorithm that we have provided, GT Sara, in a certain regime matches the best known rate that is achievable by any centralized algorithm. The rate that we have provided, or the results that we have provided, are independent of the variance of the local gradient estimator. So if you go back to this theorem, you can see that in this entire expression, nu square does not exist. We can show that in this certain regime, the rates are independent of the network topology, and these are independent. The rate is independent of the local versus global dissimilarity bias. And if this is the rate that is achieved by the entire network, and it matches the centralized rate, then the rate per node is divided by, so we have n nodes divided by little n, and we can see that at each node, the rate, the convergence rate, and the number of gradient computations that are required for epsilon complexity for epsilon accurate solution is n times lower than the centralized SARA. And this is how this is what we in the literature we typically call it linear speedup. And the distributed algorithms is n times faster than the centralized SARA. It means that it requires n times less gradient computation per node to achieve the same epsilon accuracy as the center. And these are some results on real data. On the left, I'm showing the big data regime. Recall that the big data regime is when we have not too many nodes in the network, so a small number of nodes, but every node has a very large, potentially very large number of data points, and the topology is controlled. So this is a 10 by 10 grid topology versus the IoT regime where we don't have a lot of data per node, but we have a lot of nodes. And these are typically battery operated devices where the topology is not in our control, and we compare the performance over some standard data sets of some different algorithms. With GT SARA is what we have proposed in our work. GT Saga is what we have proposed, and then distributed stochastic gradient descent, which is the simple extension of stochastic gradient descent to the distributed case, and a few other algorithms. And this is the effect of network topology. So if I mentioned before that the rates that we have derived the convergence is independent of the network topology, what it means is that in this particular regime, this algorithm GT Saga, the convergence is practically the same for all different types of graphs. So ring graph is when the nodes communicate in a ring, grid graph and the node communicate over a grid, versus a complete graph where every node communicates with everybody else. And we can see that the performance is indistinguishable, which means that in this particular regime, a network topology is kind of does not play a factor in the performance. And this is what we have theoretically shown. This is what we can experimentally observe as well. For the other measurement case where data is not available at every node in a batch, so I don't have 1,000 images, but I take measurements of the data is obtained in real time. We have shown across different algorithms that distributed stochastic gradient descent plus gradient tracking, we can use decaying step size to remove the variance, and adding gradient tracking, we have quantified how the improvement over DSGD, and especially this improvement becomes a big improvement when the data sets are not homogeneous. And we have also come up with a novel way of variance reduction where we take a linear combination of GT stochastic gradient descent and GT SARA. So beta times the local stochastic gradient. So this is just the regular stochastic gradient without any variance reduction, plus 1 minus beta times some form of variance reduction. And we can show that it the results in GTSG in a certain way it's optimal because it matches the optimal lower bound that was provided in one of the other papers on centralized methods. And it outperforms all existing methods when we chose beta under a value of beta that's not necessarily 0 or 1, which means that for online or streaming problems when data is not available in a batch but comes in a real-time way, the optimal method for variance reduction is some linear combination of the basic vanilla stochastic gradient and variance reduction. And neither one of them alone could give us the optimal rates. And this is a quick experiment where I'm showing training of 100 based on 100 points. So our goal is to find this is a linear regression problems where I would like to fit a straight line over 100 distributed points. Every node in the network, this is how they communicate, and every node has one data point. So imagine that if you have one data point, you are asked to fit a line, that any line suffices, but only the collection of the data points tells me what the linear regression line is. And if you see the evolution of these different algorithms, you can see that this is the distributed gradient tracking distributed gradient descent with gradient tracking, which converges to the true solution. This is the error keeps going to 0, right? So matches the centralized. But this is distributed gradient tracking with the constant step size without gradient tracking, where I showed you that there is always a steady state error. So it was that purple curve that converges with a steady state error. So gradient tracking allows all of these nodes to agree on the same line, which is also the optimal, versus this is distributed gradient tracking, which still converges to the centralized result, but at a very slow rate, this black curve. And gradient tracking allows us to establish linear convergence. So my summary conclusion slide. So we basically have been working on these gradient tracking based distributed optimization problems, and we have developed results for stochastic problems where data is not available in a batch at all the nodes, but it rather comes, either in a serial way or sampled from a batch. And over these different measurement scenarios, we have developed algorithms that are optimal in a way that under certain regimes they match the performance that was proved for centralized algorithms. We have shown that for online problems, the best method of variance reduction is a hybrid method where we need the standard stochastic gradient plus a linear combination with some variance reduction technique. We have shown network independent convergence behavior where the algorithm performance is independent of the underlying network topology. And we have characterized regimes where the distributed algorithms outperform their centralized counterparts in terms of the speed or the number of computations they need to achieve a certain epsilon accurate solution. My last slide, if you are interested in learning more about this optimization for especially these learning and control problems, we have a special issue in the proceedings of the IEEE, where we have several papers on distributed optimization, primal dual methods, ADMMs, etc., non-convex problems, variance reduction problems, where you can learn more on the type of problems that exist in this domain. And with this slide, I'll conclude, and I am open for questions.